Hi, Professor. Good evening. This is Uday speaking, and thank you for this time again, Prof. I think this is one of our last lectures, last assignments, and this time we're going to deal with graphical data structures and how to represent genealogy. And before even starting, I want to say that RDBMS or relational databases are not the right fit for a genealogy database. It would be very confusing. And the thing about genealogy is there's so many relationships, and RDBMS are fantastic for nodes. So if you have one node or one structure and you have lots of attributes, it's perfect. You can represent relationships too with foreign keys, but that's not what it's meant for. It's meant only for two or three relationships, and it's not meant to quickly search. It's meant for long running queries when you want to pull up piles of data and join them. But when you want to find who's the son of somebody or who's the cousin of somebody, you simply can't use these foreign keys. So RDBMS is bad. I want to share the screen now, and since this is a very I what do you say ideological what do you say assignment. It's not a programming assignment, but the design is very important. We have to design even what database we want to choose. And I want to say that I've chosen a graphical DB called Neo4j to represent the relationships. As an RDMS, would be very difficult to represent such a scenario because there are so many varied relationships. For example, from a single node, you have father of, you have son of, you have spouse of, and then you have cousin of. That's a cyclical graph, graph, and so you can't use RDBMS for this. You could use MongoDB to a certain extent because you have merchants within a merchant. eBay uses MongoDB to represent a merchant within a merchant, but not for such a genealogy database. So RDBMS would be very difficult to represent this. You could represent foreign keys, but it'd be highly inadequate to represent trees and even cyclic graphs. A graphical database, however, would be able to represent all these scenarios using nodes and relationships, and we'll be able to query the data using languages such as Cypher and Gremlin. So I've used Cypher. There's Gremlin also, which could be used. There are a few more RDS. They're called Relational Data Store. There are a few other languages, but Cypher is the most prevalent. And Professor, I saw in your assignment you've asked about data types. Here, the data types are very simple. Whereas in an RDBMS, we have to choose our data types in advance, and I totally understand that. And the moment we run out of data types, we have to change the data type from string of 10 characters you to make it string of 100. That's a big DDL change. Whereas here on graphical, most of them are string data types, and except for values for value types where an integer is chosen. But the thing is, we're going to have a automation over this, over the DB. So as the data comes in, let's say you have a data of age. The input program would utilize the integer data type implicitly. So we have a program to convert that value and store it as integer the moment it sees age. And let's say it had the address, the attribute called address, it would immediately choose the string data type. So we're not going to do it. We're going to have a machine to do it because it would take very long for us to do, and there's no need also, because it's one thing, it's very fundamental, and two, the data is coming in that's so varied. We can't have a DBA going in and creating a data type. We just can't. The data is coming. Adam is a father of Abel. Abel is a father of Cain, right? No, Abel is a brother of Cain, and Eve is the wife of Adam. So all this data is coming now. You simply cannot have a person figuring out, okay, data type of Eve is string. There's no need. We have to. It has to compute really quickly. So Neo4j is the best DB for this. Okay, now representing a human being. So if you want to represent a human, we'd represent a person as a node, and the properties would be to have node attributes and property relationships. So I wanted to say something. Node relationship attribute is like an age of a person, or the color of the eyes, or scale, or hair color. That's an internal attribute. And property relationship is that Adam owns a house. In the Garden of Eden, Adam owned a house there. or Eve also had the same house. That would be. So Adam has an attribute, and now Adam has an internal attribute gender of value male. So he has an attribute to that node called male. So that's how you identify him as a man. And he has an address of this Los Angeles, California. So that would tell us that he belongs to this, but it's not an internal attribute because it does not really belong to Adam. Adam owns that property, but who knows? He may sell it. It may go to somebody else. So we're not. So that doesn't really belong to him, but it's a property relationship. So we're going to distinctly separate these two relationships. Right from the start. Now, let's say we wanted to represent a man or boy. So representing a man would mean his gender is male and that his age is greater than 18. Otherwise, he would be a boy technically. So how would we write this law in the database, in the data structure? So if Adam has an internal attribute gender of value male, and if Adam has an internal attribute age of value greater than or equal to 18, then Adam is a man. So when you just say, "Hey, he's a man," we as human beings, we already have pre-computed it. So we already know, oh, Adam, yeah, his gender is male. Two, he's old. He's a man. He's over 18. But if you say, "Hey, this person is a boy," then immediately, automatically think, yeah, his age is less than 18, and he has his gender is male. So I want you to yes. So the thing is, we already pre-compute and we know it, right? But actually, if we tell a machine to do this, it would have to pre-compute these two attributes. What is age? What is gender? So and then the machine comes to know, oh, this is a boy or it's a man. How do we represent a woman in a graphical data structure (GDS)? For a woman, yes, the only thing that would change is the gender laws. So if Eve has an internal attribute gender of value female, and if Eve has an internal attribute age of value is less than or greater than 18, then Eve is a woman. Otherwise, if the age less than 18, then Eve is a girl. So the same way we identify, except with the attribute of gender, male or female. Now here comes a relationship son of, right? Now, we're coming to what is called implicit reverse relationships. So right now we're looking at the point of view of Adam as the man, as the father. Adam is the father of Abel. But what is Abel's reverse relationship to Adam? So that would be the reverse relationship. And as humans, we know implicitly, oh, Adam is the father of Abel. We know that Abel is the son of Adam. It's a reverse. But to a machine, we have to code it in deliberately, otherwise the machine will be totally off. So this is it. So this we call corollary. It's just an implicit inference. So if Adam is a father of Abel, then Abel is a son of Adam. This is a corollary. There's no deduction required. It's a known fact. You can immediately write it. And let's say for a daughter of Job, is Job is a father of Jemima, then Jemima is the daughter of Job. I've just taken from the Bible that Job had three daughters: Jemima, Haran, Kepuk, and there's one more daughter, and Karen. Yeah. So the thing is, if Job is a father of Jemima, then Jemima is a daughter of Job. But okay, now I'll come to this a little later. We'll discuss how we can have implicit inferences immediately because there's a better example to show. Now we're going to discuss something called marriage, the assertions. Now when we talk about assertions, these are laws that we know humanly as between for marriage. But the thing is, when we write it down on paper, or we go to the or when the couple goes to the marriage office, they actually write that X is a husband of Y. But these are actually data laws. So ultimately, you're writing it down, so it has to be data laws. So these assertions ultimately become data laws in the graphical data structure. And actually the relationship for spouse or marriage is very hard to write. Marriage is very hard as it is time dependent because the couple was married between time T1 and T2. So at that time, yes, they were married, but now they're not. A child can be born of a union and also need not belong to the same family. The child could be adopted. And the relationship is an adopted son of. So this is not the real son. Two partners could be in a relationship without nuptials, and then this is just a partner. A partner also could adopt a son. So let's look. If X is a spouse of Y and status equal to current, then X is married to Y. If X is spouse of Y and status equal to divorce at date D, then X is divorced from Y as of date D. So it's time dependent. So at this time, they were divorced on. And if they were status equal separated at date D, then X is divorced from Y and as of state D. Now, actually, this is, you may think this is an excess, but it's really practical because we need to know it's time dependent. We need to know the status, and so many laws are there regarding divorces. And yes, this ultimately ties into the laws of the land. So, what are the laws? So, these data laws are ultimately becoming the laws of the land. And they have lawsuits and separation of properties just because of these things, these divorces and separations. So these are dictating the laws of the people. Now, the data laws regarding childbirth. You can have child by marriage, child by another partner, child by adoption. So if Z is a child of union of X and Y, so this is the real union of X and Y, then Z is a biological son of X and Y, or simply Z is a son of X and Y. So the son equals biological son. If Z is an adopted child of X and Y, then Z is an adopted child of X and Y. Later, okay, so now Z is adopted and Z is also a child. So that's two relationships there. But now, what happens if Z finds out his real parents are V and W, two other people? Then, if Z is a child of union of V and W, then Z is a biological son of V and W, or simply is a son of V and W. Now, looks very weird because Z is adopted by X and Y, and now he's a biological son of V and W. So you'd have two pointers going in from two different relationships, two different partnerships going to Z, and it looks very weird, but it's very practical, and we have to represent this. Now, really assertions or relationships between people. This brings about the cyclical nature of the nodes. No, so no longer is it just a tree like father, son, um, grandfather. It no longer is a tree, and now we're connecting all the nodes. So it's become a cycle now. So we're having cousin, grandfather, nephew, niece. So it's very cyclical. So we can't use the laws of trees anymore. We're using only graphs. So let's talk about this now. There's something called reverse relationship. If you have father off and the reverse is son or daughter off. So from up it's father off and from bottom son or daughter. Now this is very natural for us to know, but we're going to represent it in data structure. So if X is a father of Y and Y has the attribute gender of value female, then Y is a daughter of X. So this is how we go reverse from bottom up. And if X is a father of Y and Y is a gender of value male, Y is a son of X. Now grandfather is interesting. If X is a father of Y and Z is a father of X is a father of Y, Z, oh, X is a father of Y. Okay. Y is the father of X, yes. Yes, this is correct. Yes, actually. Yeah, so if X is a father of Y, Z is a father of X, and Z is a grandfather of Y. So we're bringing double relationships, and Y is a son of X, and X is a son of Z. Uh, yes, Y is a son of X is a son of Z, and Y is a grandson of Z. That's correct. It's correct. Now, we're going to talk about grandson. Oh, okay, so we're going here for grandfather. Uh, Z is the father of, yes. Okay, now we're going for cousin. Forward and reverse relations are the same. So if you say X, so the definition of cousin is a little more interesting. If X is a son of W, W is a brother of Z, or W is a sister of Z, then and if Y is a daughter of Z or son of Z, Y is a cousin of X. Now this is just to say that your cousin is nothing but the son or daughter of your parents, brothers or sisters, right? But this has to be very implicitly specified in the law, in the database law. And the corollary is the same. So if X is a cousin of Y is a cousin of X, because we're not even checking the gender, so it's straight out. And if our uncle is, and here we have uncle and niece of, nephew of, So if X is a niece of Y, and Y has an attribute male, then Y is an uncle. So we're now defining the uncle. And if X is a nephew and Y is attribute male, then Y is an uncle of X. So now this is both for niece and nephew. We're doing it, and in the above, only the gender of Y is in question, not X. The gender of X is determined by the word niece and nephew. So by just using the word niece and nephew, we're automatically determining the sex or gender of the person. So if X is a nephew of Y, X has an attribute gender of value male. So immediately we are already computing that the gender of this person X is male, and if X is a niece of Y, X is a attribute gender of value female. This is before we even connecting. By just using the word niece, it automatically specifies that the gender of a person. So if uncle, and we're doing auntie now, if X is a Y, X is a niece of this, and Y is the attribute gender, then Y is an aunt. So it's just the gender that's changing, but that's how we define relationships. So this is the assignment. These are the assertions, and it produces a wealth of information. And we cannot use an RDBMS. We have to use a graphical data structure, and I'm choosing a Neo4j, which is quite adequate to represent it. So I thank you, Prof, for your time, and thank you again for letting me submit later. And I hope you like this. Thanks, and have a nice day. Bye.